Today we are going to finish the chapter 2, and last class I have teach you how to apply the bulk modules to understand the volume changes of the liquid under compressed process. Okay, so this is our exercise in last class. And right now, I'm wondering to move the topic to the stress. So there are two types of the stress. As you can see here, we have the normal stress and the shear stress. So in fluid mechanisms, the normal stress is usually associated with the fluid weight. So we call that the pressures. So after these chapters, we will always call the pressure force is caused by the normal stress. Okay, especially for the fluid. And as we know, the shear stress will cause the fluid start to flow. Okay, before in previous class, I teach you the shear stress applied to the fluid, and the fluid material cannot broken, only to be the flow behavior. Okay. So the slide just define the stress can be represented by the ratios of the force and to the associated areas. Okay. And in this textbook, we always use the tau represent the shear stress. And then we use the P related to the pressures. Okay, so before we would like to convert the pressure, the stress, or the shear stress convert to the force, we should understand the pressure distribution first. And which is the pressure will varies along the point by point of the target surface. So this is an example. You can see very clearly the flow direction is from the left to right. And we can see there is a large pressures distributions in the front. And there is a lower the pressures in the back. Okay. So this is a very famous pressure distributions for the Ch2.Fluid problems. So this is just a video. Sometimes we know that the pressure distributions in the flow will controlled by the flow conditions. So the flow conditions such as the flow depth, how large it is, and what is the flow velocity on the surface. Okay. So I can show you one of the movies. You will know. For our problem, sometimes we will do the modeling first. And this modeling, you can see the color showing here is the flow velocity. And you can see the color indicate the different flow velocity speed on the surface. So if we have some bridge and we have installed some pier structures along the rivers, and we should calculate how large pressure distributions under different flow conditions, because sometimes the flow condition is quite larger, and the pier structure will be broken, right? So we should understand it first. So in that case, we know that where is the large pressure we have, and if we go back to see the slide, we actually know it's depend on your flow directions, and in front of the structures will have the larger pressures. So this is just the photo on site. We can see that the pier in here, and there is a larger turbulent flow. Here will result the higher pressures. And in typhoon period, sometimes the structure will be broken and your bridge will collapse. So it's a very dangerous problem. Okay, so when we understand how distributions of the pressure, and sometimes we will apply the integration operators to compute the final force we have. Okay, so this is a very normal operations when we calculate the force from the pressure distributions. Okay, so this is just a slide show how can we deal with the integrations. So for the normal stress, as we always mention in the following class, we call that the pressures. And we wondering to calculate the pressure force. And you should actually know the pressure factors multiplied with the normal factor of the associated service. But we always see the negative sign in here. It indicates the pressure directions is always opposite with the normal factor of the service. As you can see, this is a normal the pressure stress, right? But the normal factors of the associated service is opposite directions. So we need to have additional negative minus sign in here. But for the shear stress, we don't need the minus sign because the shear stress is always parallel to the tangent factors along the associated service. So we don't have any negative sign in the shear force problems. Okay, so the table just summarizes all important force we'll teach in the following class. So totally we only have the 7. Okay, as the previous class I mentioned how many properties we have in the class. So for all of the tables shown on the slide, you should keep in mind some important properties. So 7 forces are pressure, shear, buoyant, and surface tension, drag, lift, and thrust. Okay, so today we are focused on the shear force first. And as we know, the shear force caused by a shear stress distributions. Okay, and sometimes the shear stress is related to the viscosity property. So we can also call that is the viscous force. And after we teach the shear stress, and then we will move to most important thing in this chapter is the surface tension force. And how about the physical phenomena associated with the surface tension force, we will know in the following slide. Okay, so right now the topic is the shear stress. And what are the important equations we have and associated with the shear stress? So this is a very simple equations as you can see here. We're trying to relate the shear stress to dynamic viscosity, and the second item in here is the velocity gradient. So this equation, we call that the viscous equation. And we can also call that is the Newton's law of the viscosity. Okay, this is a very important equations. As I always emphasize, the shear stress in fluid material are the behaviors are similar to the friction force in solid body. Okay, so we are trying to figure out how large it is for the shear stress, and we actually know the viscosity equations tell us the shear stress is equal to the viscosity multiplied by the velocity gradient. So if we would like to calculate the shear stress, we should have the velocity field. If we don't have the velocity field, we cannot compute the velocity gradient. And when we compute the velocity gradient, you will often need to apply the non-slip condition assumptions that indicate when fluid in contact with a solid body, okay? And the velocity of the fluid at the point of contact is the same as the velocity of the solid body at the same point. Okay, so you may not really understand what the meanings in here, but you actually know the behavior is no slip condition. Okay, so I can show one of the movies. You can figure out what I mean in the no slip conditions. So you can see this is a circle container, right? This is a circle containers. And as you see, we put some fluid inside. And at the boundary interface here, this is the boundary between the circle containers and the fluid. And you can see the circle container is rotating, and the fluid at this point also move together. So that means there is no relatively motions between two materials. And in that case, at this point, we say that is no slip conditions. Why no slip? Because there's no relative movement, right? So we call that the no slip conditions. Okay, so if we go back to see, this is a very important assumptions when we compute the velocity gradient. Why we need to compute the velocity gradient? Because we would like to calculate the shear stress. Okay, so this is another example show how can we compute the velocity gradient. And sometimes we call the velocity gradient is the rate of the shear strength. The rate of the shear strength. Okay, so the key knowledge is we should know the velocity first, right? If we don't know the velocity as function of the spatial dimensions, how can you calculate the gradient? Okay, so this is one example. This is the pipe. Okay, we have the pipe. This is a round pipe. And the flow in the pipe, flow direction is from the left to the right. Okay, and you can see there is a velocity profile we assumed. So this is the true conditions. The velocity profile in round pipe is always the parabolic shape. So we have the velocity functions along the y directions. So these directions we can call the y directions. So you actually know along the y directions we have a different velocity values. So that means if we know that the parabolic function shape and we have the velocity functions and we know that the velocity as a function of the y-axis, so we can easily to compute the gradient we have in here. So that's why the velocity dv dy is our gradient values, because the functions, the velocity will change the velocity values with the different y direction axis positions. Okay, so you may not know where is the large gradient we have along this profile, but we actually know in the centers, along the pipe centers, okay, there is the largest velocity. And at the boundary, okay, there is no any fluid velocity. Okay, just based on the velocity profile in here. Okay, in the following class, I will teach you how can we calculate the velocity profile like this shape. And the next slides, I just tell you what the gradient means. So we actually know the gradient because we already learned how in differential idea in calculus class. So the gradient is quite simple. We just gradient equal to the slope of the tangent line, right? The gradient just is the slope of tangent line. Okay, so we know already the parabolic function in here. So at the center's point in here, we can draw the line, the tangent line, and calculate the slope of the line. And we actually know the slope at this point is equal to 0, right? That means in there is no shear stress, because we know the shear stress is proportional to velocity gradient. If there is no velocity gradient, so no shear stress at this point. Okay? So in the same way, we can try to figure out if we do the tangent line at the wall, the point at the wall, we should know that the tangent line, the slope here, is the largest one. So that indicates at this point, we will have the largest shear stress. Okay? So you can try to connect the largest shear stress will result no velocity. Okay? Because the shear stress is the friction for the fluid material. So the largest shear stress, we will have no velocity at this point. And because at this point, there is no shear stress, so the flow velocity will largest in that point, because you can figure out there is no friction. So that's why along the center of the pipe will have the largest velocity. Okay, so this is a very useful equations we can, if we have the velocity field, and we can calculate the gradient and multiply the viscosity. Why? Because I tell you the viscosity is very important physical property in fluid mechanism. Largest viscosity, we will result the large shear stress, right? Because the fluid is difficult to move due to the large viscosity. Okay, and so that's the idea. So we should try to do some exercise to understand what we are trying to figure out all the shear stress distribution along the pipe. Okay, so I highlight this example. We call that the polysular flow. Okay, what is the polysular flow? The polysular flow just the laminar flow. Just a laminar flow in a long pipe. Okay, so you see there is a laminar flow in the long pipe, and we call that is the polysular flow. And because this is a polysular flow, so we actually know the velocity can be represented by the velocity as function of the radius, because this is a round pipe. So the radius can indicate the locations along the pipe, right? So as function of the radius will equal to the V0 is the constant velocities along the centers of the pipe, and multiply the 1 minus the R divided R0 square. Okay, so this is our velocity field. We actually know the velocity field, and we just trying to figure out what the condition we already have. So you can see the exercise we have. We already know the pipe diameter is the 4 centimeters. Okay, so we should know the R0, because the R0 in here is the radius, and we know that the diameter is the 4 centimeter. So that indicates the radius should be equal to the 2 centimeter. And we convert the centimeter to the meter unit. So 0.02 meter. Okay. And the velocity along the centers, we also have the condition is equal to 1 meter per second. Okay. So we know that the velocity flow along the center pipe is the 1 meter per second. Okay, so what's the problem we should answer? So if you go back to see, the problem is please calculate the shear stress. Calculate the shear stress, but at the different points. So the first, we should calculate the shear stress at the center point. As you can see here is the center. And the second, at the wall boundary, okay, at the wall. And the final is, please calculate the shear stress when our locations at the 1 centimeter. Okay, so totally we should answer the 3 shear stress at the different point locations. Okay, so we go back to consider what we have already is, we already know the knowledge is the viscosity equation. Okay, so we write down our viscosity equation. We know that the tau will equal to the dynamic viscosity multiply the velocity gradient. Right now the velocity field as function of the radius, and we should have the dr, right? We should calculate the derive the dr. So dv dr we should calculate the first. Okay, so for the mu is the constant value, so we should know the conditions of the fluid. As the exercise highlight, the fluid is the water and under the 15 degree. And we always remind you, you don't need to remember the actual values of the viscosity, because I will provide the table, and you can check the values from the table. Okay, so I have the table on the right hand side, and I know that the 15 degree, and then we have the viscosity value in here. And always remember, right now the mu is dynamic viscosity, not the kinematic viscosity. Okay, so you need to know what the viscosity you need for the equations. So we can write down the number we already have is 1.14, and the 10 minus 3 powers, and the units, the Newton seconds per meter square. Okay, so we got it. We checked from the table, so we have known how large of the dynamic viscosity. So the seconds, I will try to calculate the velocity gradient. So I trying to do the differential, the v with the radius directions. Okay, so that the dv dr, you can, based on the equations, you can calculate the number is the -2, and keep the inside parameters r divided r0, and we should partial differential with the r. So we have the additional constant value is r01, right? So we can try to calculate the differential values based on your knowledge. Okay, so we can rewrite this equation is 2 times and r divided r0 square, right? Oh, sorry, we still have the one constant v0 in here, right? Because there is a v0 outside. So we have the additional v0 values. Okay, so we have the v0. Okay, that check the 2 minus v0 multiply r0 over r, and the partial differential with the r0 r is equal to the constant r0 over 1. So we have the velocity gradient can be represented by the number showing here. Okay, so after we calculate the velocity gradient, so we got it. We got it the velocity gradient, and we can try to build out the formula for the shear stress. So again, we based on the velocity viscosity equations, we know that the tau equal to the mu. So right now we actually know the mu is 1.14 and the 3 minus 10 minus 3, and the Newton seconds per meter square. and then multiply the velocity gradient is the -2, right? -2. And we have the R. We don't know where is the R. So we keep the R. It's our unknown parameters. And we actually know the R0 is 0.02. And we should have the square. And then right now the dimensional units is a meter square, right? It's a meter square because R0 square. So the meter square units. And what's the velocity is the 1 meter per second. So we have the velocity 1 and the meter per second. Okay, so based on these equations, only one unknown parameter is the R. Okay, so we can calculate all the number we have, and we can represent the shear stress as function of the radius. Okay, and then after that, we can put the R values to consider different location, how large the shear stress we have. Okay, so use your calculator to compute the constant number here, 1.14 divided 1,000 and multiply the -2 and divided the 0.02 twice times, okay, and multiply 1 meter per second. So the number in here is equal to the 5 minus 5.7. And you can do some dimensional balance. You can see we only have a Newton, and this is meter cubic, and this is a dimensional, and we still have additional R. Okay, still have additional R. So if you put the R inside the equations, so the dimensional will change to the Newton per meter square. So it's a constant dimensionals compare the right hand side and left hand side. Okay, so this is a very important result, because later we are trying to consider different conditions, different locations. Okay, so first we go back to see our questions. First, we would like to calculate the location is R equal 0, right? Because the first questions we need to answer is the location at the center of the pipe. So at the center, so we don't have any radius. Okay, so R is equal to 0. So we put the value back to equation showing here. Okay, and then you know that, okay, there's no shear stress, right? So we found out the first answer solutions for the first questions. Okay, so we move to the second try. The second, we actually know the condition is at the wall. So we should at the wall. And what's the radius at the wall? So the radius at the wall should be equal to the R0, right? And the R0 is 0.02 meter. So we put the number inside the equation. We can calculate how large the shear stress we have. Okay, so how large shear stress we have? We can minus 5.7 and multiply 0.02. Okay, so this is we calculated the tau equal to minus 0.114 and the Newton per meter square. Okay, so this is the condition for when the radius is equal to the 0.02 meter. Okay, and then the final ones, we wondering to calculate the positions of at the R is equal to 1 centimeters, and that will equal to 0.01 meter. Okay, so in that case, we can calculate the shear stress very quickly based on the equations. So we know that this will equal to the minus 0.0 0.57 Newton per second per meter square. Okay, so that's the result. Just figure out at the center of the pipe, there is no velocity gradient, so we don't have the shear stress at that point. That's why always we can see the highest speed at the center. Okay, but at the boundary in here, the wall, there is the largest shear stress. That's the reason why we cannot observe the velocity speed at the boundary location. Okay, so this is a very simple ideas. We based on the viscosity equations, okay, showing here, and the major knowledge in here. If we don't know the velocity, how can we calculate the shear stress? So we should know the velocity first, and then we can calculate the shear stress. But the shear stress also corresponding to viscosity property. So if you don't know what kind of fluid you have, you cannot understand how large the viscosity. So in our case, we actually know the fluid is the water, and at the certain conditions. So we can check from the table for the viscosity properties. Okay, so this is the normal conditions in the future when we have some hydraulic problems. We're trying to figure out how large the shear stress we have, okay, in our conditions. So the sequence is a very important properties when we apply the viscosity equations. So the viscosity equation also will be helpful for identify the fluid type. So there are two fluid type, Newtonian and non-Newtonian. So how different they are? You can see I plot the one figures in here, and the x-axis, the property is the velocity gradient, and the y-axis is the tau. So you should understand the slope of this line is equal to the viscosity. Okay, so we just put the velocity gradient as the x labels, and the y label is the shear stress. So that's we forward to know the slope is the viscosity. So I directly tell you if the fluid is Newtonian fluid, and the behavior in here, you can see the linear relationship between shear stress and the velocity gradient. Between the shear stress and the velocity gradient. And one thing you need to know, there is a close point that indicates this relationship with the zero intercept values. So you cannot, this is a close 0 point in here. There is no intercept. Okay, there is no intercept. So in future, if you do some test and then you make the plot for any fluid, you can see, if you can see the linear relationship between the velocity gradient and the shear stress, and we can directly call that fluid is the Newtonian fluid. Okay, and I just highlight some material are the Newtonian fluid, as the air and the water are the Newtonian fluid. So if we understand what the meanings of the Newtonian, okay, just keep in mind the linear relationship between the shear stress and the velocity gradient. So the next slide, I want to tell you what is a non-Newtonian fluid. Okay, so there are the three types fluid associated with the non-Newtonian. Okay, and the first one is shear thinning and shear thickening and the Bingham plastic. Okay, so as we know, if we call that is a non-Newtonian fluid, that should be the non-linear relationship between the shear stress and the velocity gradient. Because we have no Newtonian fluid will have the linear relationship between each others, and there is no the line will cross 0 point in here. Okay, so if we focus on the shear thinnings, the viscosity of the fluid decrease as the rate of the shear strain increase. Okay, in here we just call that the rate of the shear strain is a velocity gradient. Okay, why the viscosity decrease as the velocity gradient increase? So as I mentioned in previous slide, velocity gradient will equal to, you put the tangent line and calculate the slope. So I put 1 point in here, and I can make the tangent line. Okay, this is a tangent line, and the slope is the velocity gradient. And if I make another point in here, and I make the tangent line again, not actually tangent, but you can see the slope totally change, right? And the slope will decrease when the velocity gradient increase at this point. So you see the slope will decrease as the velocity gradient increase. That indicates the slope is viscosity. And the slope will decrease when velocity gradient increase. Okay? So that the velocity gradient increase result the lower dynamic viscosity. That indicates the fluid much easy to flow. The fluid much easy to flow, right? Because the lower viscosity, higher movement for the fluid. So I just highlight one catch chart. It's related to the type of the shear thinnings. If we remember the ketchup, you mix with the waters, and the ketchup will flow, right? If you don't mix with the water, that just stand at the table, the ketchup didn't move. So that's why you mix the water with the ketchup, and the velocity gradient will increase, and result the dynamic viscosity decrease. So the fluid will much easy to flow. Okay, so and in the same ideas, if we focus on the thickening, and that's the curve in here. So you have additional curve in here, and then you know that when the velocity gradient increase, the slope of the line will also increase. That means the shear thickenings will result the higher viscosity, because the velocity gradient increase, the slope also increase. Okay, so in that material, you know that the viscosity increase with the velocity gradient increase also. So I also highlight one material, starch. As you see the starch like the gas, right? And the paper particle. And if you mix the water with the starch cannot move. Okay, just stand on the table. So that means you mix the water with the starch, and the velocity gradient increase, result the dynamic viscosity also increase. So the motion behavior will decrease because the viscosity increase at this condition. Okay, so the final one is the Bingham plastic, which acts like the solid. You see, like the solid first when the small values of the shear stress but then behaves as the fluid at the higher shear stress. So if you focus on the line in here, this is a Bingham plastic. And there is the, as you can see, there is a jump. So we have the intercept value, right? There is a jump. So if your shear stress is lower than this point, the material will be the solid. If your shear stress higher than this point, and the material will become the fluid. Okay, so that's the Bingham plastic material that indicates the different shear stress condition. The material property will change different phase. The small shear stress will have the solid behavior. If the stress higher than certain threshold, and the material will become the fluid behavior. Okay, so the Bingham plastic is a difference behavior under different shear stress condition. So I just highlight some material like the mayonnaise and the toothpaste. You can see different shear stress, they will have different behaviors. Okay, so that's totally 3 types materials associated with the non-Newtonian fluid. Okay, so these figures I put here is very famous. When we interview some student apply the master degree, and we will also ask the questions, always ask the questions. Can you say something about Newtonian and the non-Newtonian fluid? How different they are? Do you know what the physical meanings about the non-Newtonian fluid? So, but most of the students forgot everything and cannot answer the true answers. Okay, so but for me, you should keep it in mind because this is very important physical properties for the fluid. Especially, you need to know how can we distinguish Newtonian and the non-Newtonian fluid. Okay, so the slide I wondering point out a special case of the viscosity equation. So we call that the Coulter flow. So what are the meanings? If you see the condition for the Coulter flow, we put the stationary wall on the bottoms, and on the top, it is the moving wall. And the moving wall of the velocity is the V0, we assumed. And as you know that I highlight, there is no slip condition, right? So when the particle move in here, and the fluid will have the same flow velocity with the solid body. Okay, so this is the point. We should apply the no slip conditions. And there is the y-axis, and we mix some material between the two walls, and we actually know the thickness is the H. Okay, so this Coulter flow usually we apply to understand the problems of the duplication problems. Okay, so you can see some words highlighted in here. The duplication is very important in our life. Sometimes we will mix some duplication material, and we can help some particle will moving quickly. Okay, so but what I would like to emphasize, this is a special case of the viscosity equations, because as you can figure out, we can see the constant. This is a linear velocity profile, right? So what are the effects of the linear? This linear velocity profile, which indicates the slope along the y directions didn't change at the different location point. If in that case, we go back to see how can we compute the velocity gradient along the y directions, because the velocity is the linear functions along the y directions. So that indicates we always have the constant value of the velocity gradient. We only need to know how thickness we have for the materials, and we only need to know how the velocity on the moving wall. And we always have the constant velocity gradient, which indicates we always have the constant shear stress, right? Because the dynamic viscosity didn't change because we keep the same material on site. Okay, so that's why I call it is the special case, because this is when we see the Coulter flow for the replication problems, and we always can say anywhere at the replication material with the same shear stress, because the velocity gradient didn't change at different locations. Okay, so this is very important ideas. So we have the exercise, and we can figure out how can we apply the Coulter flow. So the previous slide, we have the Poiseuille flow, indicate the laminar flow in the long pipe. And here we call that the Coulter flow. We are trying to apply a special case for the linear velocity profile to predict the shear stress. So that idea, what is the shear stress at the locations of the moving wall? So this is the answer we should, the question we should answer. Okay, so go back to see how the parameter we have already. So first we have the, we know that the moving wall is a location at the y equal to thickness of the replication material. And the second, we know that the moving velocity V0 is equal to the 10 centimeter per second, and it will equal to 0.1 meter per second. Okay, and we actually know the thickness H in here. We know that is the 5 millimeter. Okay, and the 5 millimeter is equal to the 0.005 meter, right? Okay, so we have the thickness of the replication material, and we have the velocities, moving velocities for the top of the moving wall. And the questions tell us the dynamic viscosity for replications, mu, okay, we have is equal to the 0.036 Newton seconds per meter square. Okay, and we know that the Coulter flow with the constant velocity gradient. So we can apply the viscosity equation. We know that the tau will equal to the mu, and because the linear profile in here, we have a linear profile, velocity profile in here. So the gradient always the constant value is V0 divided the thickness of the replication. Okay, so the question is very simple. We just put all the number we know right now and to calculate the shear stress. And we didn't to consider what the point we have. Because at anywhere, they have the same shear stress. Okay, so we directly calculate the number 0.036 Newton seconds per meter square, and multiply the V0 is 0.1 meter per second, and divided the thickness is 0.005 meter over 1. And you can do some balance unit. You can cancel out the meter, second. And the dimensional in here is also equal to the Newton per meter square. It's a constant dimensional after we check. Okay, so use your calculator to compute the final answers. And just double check the number is correct or not. So we have the 0.72 Newton per meter square, and this is the same answers compared to the right upper corners in here. Okay, so when you consider the different material, if we wondering to have the high speed of the velocity in here for the moving walls, how can we change? Okay, we can change the material with the lower viscosity, and we will have the higher moving speed if we fix the shear stress. Okay, another way is we can decrease the thickness of the lubrication, and the shear stress will increase. Okay, so you can adjust which function is the best fit your purpose. Okay, sometimes we will replace different lubrication material. We will have different behaviors. Okay, or sometimes we just change the thickness, and we will have a different moving velocity. Okay, just based on what the purpose you want. But the idea for the cool-water flow, the shear stress at all points in cool-water flow is always constant, because that anywhere with the same are with the same velocity gradient. Okay, just based on viscosity. Okay, so we may stop here, and maybe we will go back in the next class. Okay.